Okay, this. So files. Anyway, I will draw the circuit. Oh, something wrong on. So something like this was the. Okay, we'll solve it again. So it was having. So we are required to produce a flux of in a air gap 2.5 milliweber. Yeah. All other things are same. Only what I did, I changed the coil position. Okay. But maintaining all other things same. So this is the air gap of 1 mm, and you know the other details, they are same. Okay. So what so in the flux here is same as that of previous case, as that of previous. So whatever was the MMF for air gap, and this, I think this was named as a C length, C. So MMF for air and MMF for C. Okay. What are the values? Anybody, can you put in a chart? Can you put it in a chart? It was 324, sorry. For air, it was 795.6. 795.6. So 795.6, and for C it was for C it was 270.
270.
270. 270. Okay. 71. It what was the value? Or just 270. Clear?
Exact
Now
270, sir.
okay. Now what I did, I put a coil over here. Okay. Now if I plot if I plot a curve for the data given, from that I get the mu r. Okay. So now actually we need a graph paper and plot it on that. Clear? So anybody having graph paper with them, they can do it very immediately. Okay, I think for E, for B and H, I will try 0.2, 300. So 0.5 will be somewhere here. So it is 540, so somewhere here. And for 0.7, if I do that, it will be something like 650. So this is 300, 540, 640 somewhere here. Okay. And for 1 it is 900. So almost somewhere here. Or 1 somewhere here. So if I plot this, if I plot this something like this, this is 1, how much? 9, and this is 1. So what I will do, just now, because I don't have a graph, anybody tried? Tried or not? So just, it is not a correct or very good method, but what I will do, I will choose the 0.7 and 1b, that is the range which comes out to be difference is 0.3. So change in B is 0.3, and for that same change in B, the change in H is, this is very crude method, but since we don't have graph paper, now we are using it. Okay, so del B is 0.3 and del H is how much you get? 250 or 350? 250. Okay, this is how much? 900 minus 650. How much you get? 250, na? Okay. Am I audible?
Yes, sir.
Yes, sir.
Get the mu equals to
Yes,
B
sir.
by H. Okay. So from this value, that B is 0.3, 0.3 and H is 250. So from that you get the mu value for this iron material. Got? Okay. How much you get? Arre, ruko, ruko. Don't put more. So it is gain. It is 0.0012. Okay. 0.0012. So okay. Now you got the mu. Then it's a very simple way. What you can put, what you can do. Okay, MMF for this is known to you. Clear? MMF for this total path, which will be coming across this, I think it was named as B or A, I think it was B, this portion, 60 centimeter. Huh? This was named as B. Clear? And the MMF,
And MMF.
array, mute karo, mute yourself, it is repeating. So the MMF for this B portion will be same as MMF air plus C. So it is which is 795, I think. 795.6 plus 270. This is the MMF. Clear? So approximately it comes out to be 1000. कितना आता है? 1011. It may be. No. 800 to 70. So 1060, something like that. How much?
5.6.
It's 5.6.
065.6.
1065.6.
Okay. You got this. Now, this same MMF will be across this. Clear? Same MMF will be across this. Now, from you can calculate reluctance of a B. How? You know the length upon mu by mu into area of that. Is it not? So, length is 0.6. It is a 60 centimeter. You got mu value from here. So, it is 0.0012. And what is the area? It is 25 centimeters square multiplied by 10 raised to minus 4. Clear? So from this, what you can get? The value of SB. Okay. After getting the value of SB, after doing calculation, can you tell the value?
Twenty into 10 to the power 4.
Put in a chart, some audible issue. 20. Put it in a chart. Okay. Now, after getting the value of SB, clear? You know phi into S is MMF. Okay. You know the MMF across B portion. MMF across B. Okay. So MMF across B, you know the SB. You after getting calculations, you get the value of phi B. Okay. You get the value of phi B. Okay. Now, after getting the value of phi B, do the calculation and tell me you got the MMF B value, you got the SB value from this. So what is the value of phi B?
5.32 into 10 power minus 3.
See, put it in a chart. That is better. Hello, chart. You are not putting the value of SB. Any issue with the chart? Let me check. Oh. This is a reluctance value, I think. Any more? Five, 53 point, so I'll make it 5.328 into 10 raised to minus 3. Okay. So this much milliweber you will be getting in the B. So you know the value of a flux in this path. You know the value of a flux in this path. And applying Kirchhoff's law, what will it happen? I can put the circuit like this. This is my MMF. Here you have air gap C and this P. So this is B, this is air, and this is A portion, if I name this as A. Okay, so MMF at this, after getting MMF at B, and after getting reluctance calculated, you can calculate the value of phi, which comes out to. So what will be the phi here? So if I name this as a phi 1, this as a phi B, then the total phi is phi 1 plus phi B. Okay? Phi 1 plus phi B. How much value you get? It is something like 7.828 milliweber. Okay? 7.828 milliweber. Clear? Anything wrong in calculation? Is it correct? Slow hai kya? Correct. Na? Now, after getting this value, now you got the value of phi, total phi. As you know, the path A and path B, they are of the same material and are identical in geometry, having identical geometry. So their reluctance will remain. Same or not? They are of the same material, same
Yes, sir.
dimensions. So the
Same, sir.
reluctance SA will be equal to SB. Okay? The reluctance of SA, this, and reluctance of this will remain same. So now from this you can calculate the MMF for the A. This will be equal to SA into phi. Phi is the flux in this path. Phi is the flux in this path. Clear? So what is the value you get? 7.828 milliweber. And what is the reluctance? Have you not calculated SB value?
2 into 10 to the power 5.
Okay, correct. 2 into the 10 raised to the power 5. Okay. I am assuming correct answer is told to me. I am not rechecking for the calculations. So got it?
Yes, sir.
So now what is the MMF for this? Do calculation.
564.
Huh?
1564, sir.
1564. 1564. So now you can apply Kirchhoff's. You can apply Kirchhoff's for this Kirchhoff's loop, Kirchhoff's voltage law for this loop. Okay. So now you can add the MMF of this required MMF or total MMF. You can say it is MMF for A plus MMF for A plus MMF for air plus MMF for C. Here, MMF for air plus MMF for C. So what is the total MMF you get now?
2631, sir, approximately. 2631.
2631.
1.
2631. Okay. Is it correct? Okay. So total MMF,
261.2.
total MMF is 2631. What was our question? Find the required current. Am I right?
Yes, sir.
Yes, sir.
Yes, sir.
So now this total MMF will be supplied by our source, which is 2631. Okay. And this is equal to N into R. So now you have 1000 tons, I think. Am I right? I have put 1000.
Yes,
Is it
sir.
okay?
Yes.
Yes, sir.
2631 upon 1000. So how much current you require? 2.631 ampere. And what was the previous answer?
1.3896 ampere.
So what you conclude from this? What you conclude?
Current
Changes.
So if I change the position of a source and maintaining other condition constant, unchanged, there will be a change in required MMF for the same condition. Huh? Understood? It may increase or decrease. It may increase or decrease. In this case, it is increasing. That is different thing, but it will change. Okay? Because now this is the main source. Earlier, this was here. It was a coil, so it was a main source, and this was distributed like this. So I hope you have understood how to solve this circuit. Okay? Just 1 minute. Okay, now I give you one. See, I have a cast steel ring. I'll just draw the circuit first. That will help. Here or otherwise you can control A. So I have got this type of a ring. Okay. Clear? And this is here I'll be putting color. So say this. I have got another material here. Okay. And this is 18 centimeter high. Okay. This ring has an external diameter of 24. This is external diameter 24, all in centimeters. And this is having a square cross section. Where is that? This is made up of a square bar of 3 centimeter square bar. And this is 18. I write the dimension for this bar here. It is 18 by 3.4. Okay. So all in centimeters. So it's fitted. So I want to produce flux density B in this. this portion equal to 1 Weber per meter square. So you have to find how much MMF you should apply here. This. So how much? This is the coil. I am putting coil on this side, and in another half I need this much density. So find out. I will give you the BH values like this. This is 1 is 900, 1.1 is 1020, and 1.2 1220. This is for this outer ring, or I can put this as a cost steel, CS. So for CS, these are the values, and I put this as a CI. Or something like this. Iron I'll put. This is my iron. So for iron, I have this 1.2 590, 1.4 1200, and 1.45. It is 1650. So this is the data for iron. This is data for that outer link cast steel. Okay. Now you have to calculate how much ampere turn should be, or MMF, generated by this coil, so that you get a plug density of 1 Weber per meter square in another half. Okay. So if I put the coil on this side, I need 1 Weber on this side. Or if I put a coil on this side, I need 1 Weber on this side. Okay. So you have to find out the required MMF of the coil. What should be the MMF of the coil generated by the coil? So do it on your own. Hello? Any issue?
This middle, it is in this middle cell, it is cylindrical cuboid shape.
I'm not getting you. There is a breakage. Put your question in a chat so that I will be able to answer. Hello? Put your question in a chat. I'm not getting. No, actually, these are the dimension. It may not be cylindrical or it may not be cuboid. It may be anything. Okay. This is 18 centimeter by 3 centimeter by 0.4. So the height is 18, 3 centimeter. It's a bar. You can assume 18, 3. You can assume something like a rectangular bar. Okay. You can assume rectangular bar. Clear now? It is something like this. I will draw the diagram just for understanding. Here, it is like this. So this is 3 centimeter. This is 18 centimeter, and this width is 0.4. It's all in centimeters. Huh? Now it is clear?
Sir, 24 is mean or is it the outer diameter?
Uh,
The 24 is the mean diameter or it is the outer
I
diameter?
told you it is outer. It is clearly indicating outer ends. It is
Yes,
clearly
sir.
indicating outer ends. If it's
Yes,
an
sir.
average, it will be shown something like this. I'll just. Oh. See. Oh, if it is. See, these are the inner, external, inner. If it's average, the dimension will be shown like this. There will be center to center.
Yes, sir, I got it. I was a little bit confused. Sorry, sir.
Sir, how many turns are there in coil?
No, you simply find out the MMF. No need to find the current separately. Okay, what? See, this outer diameter is 24. So this is, what will be the inner diameter? Outer diameter is 24. And what will be the inner diameter?
15.
18.
It is 18. So average diameter is
21.
24 plus 18 divided by 2, which gives me 21. So length will be pi into d, average. So which comes out to be 66 centimeter. Am I right? Okay. So the length of, so here the length of the half of the ring will be, what will be the length? Length of the ring
2 pi d by
33.
33. Is it okay? 33 centimeter. Now you know the length. You know what is the required density? 1 Weber. This is count. I think cast steel. I said it's immaterial whether you call cast steel, cast iron, cast something like that. Any kind of a casting. So for the B equal to 1, for this this what I call cast steel, there H is 900. Okay. So you can calculate the MMF for this portion. I'll just name this as a B. Okay, MMF for this B will be 900 into length, H into L. Is it not? This is H into L. So how much you get? Around 270 or 300. 297. Okay. So you have calculated the MMF for this portion. Clear? Okay. Now the same MMF will be applied across this. You know? Same MMF will be applied across.
Yes, sir.
Clear? See, I told you to keep your mic muted, but somebody is putting and there is a, what I say, revision. Okay, now same MMF is applied here and you know the length of this. What is the length? 18. So what will happen now? What is the length? Length of the, I can name what I name this. You can take this as a C. Yes. So what is the length of the C? Length of the C is 18 centimeter. Clear? Or 0.18 meter. Okay? Okay. So the MMF. So what MMF for C will be 297. Is it not? It is same. There is no air gap. It is assumed that there is no air gap at the joint. 297. So from this you get the H for C. H for C. Calculate. Are you getting anything or you have to plot the graph? How much you get?
1650.
1650. And if you find a standard data, you no need to plot a graph in this case because you are getting standard value. So what will be the value of a B? What will be the value of a B in the C? It is 1.45. Now since you know the B, you know the cross-sectional area. You know the cross-sectional area. So flux in C will be how much? B into A. Huh? Now B is 1.45. And what is the area? Area is 3 into 0.4 and into 10 raised to minus 4 because it will be in centimeter square. So to get exactly into meters, I have to multiply it by 10 raised to minus 4. So what is the value of flux here?
1.74 into 10 to the power minus 4.
Okay, 1.74 into 10 raised to minus 4. Okay. So now what
Sure.
will be the total flux in this portion of a coil? Flux here will be flux through this and flux through this. Is it not? Okay. Okay. So what is the flux through this? You know the density. You can multiply it by the area. What is the cross-sectional area of this? It is a square of 3 centimeters. So it is a 9 centimeter square. So the cross-sectional area is 9 centimeter square for the big ring or CS. And for iron, it is 3 into 0.4. So now you got the B here is 1 Weber per meter square. So when you multiply B by the cross-sectional area, you get the phi B. So what is the value of phi B now? Phi B will be 1 into 9 centimeter square. So it is 10 raised to minus 4. Clear? And what is the flux here? 1.74. So what will be the flux in this main ring or over which your source is available? Source. Okay, it is. I'll just put this as a 9. 10 raised to minus 4 is a common. So it is 1.74 plus 9 into 10 raised to minus 4. Okay? Into 10 raised to minus 4. So, or otherwise you can put it equal to 10.74. 10.74. Clear? Am I right or not? Sorry, I did miss some 10.74 into 10 raised to minus 4. So the total flux here, if I name this as A, let us say, then this will be flux in A. So from this flux in A, okay, you can find out what you can find out. You can find out density in A. How? Phi divided by area. So now the density in B, density B in the part A is how much? 10.74 into 10 raised to minus 4. This is the flux. And what is the area? Area is 9 centimeter square. So it is 9 into so. What is the density you get now here in the A part? How much you get? कुछ आएगा ना
1.1
1.1
19
one more digit 3. Is it okay? So this is there. Now you find here, this is a outer ring. So it is of cast steel, CS material, and you don't have the value 1.193. So you have to plot the graph here for this and get the value for 1.193. So it is 1.2 available. Now we don't have a graph paper, so I will approximate it to say something like 1200, just for understand. So for 1 point, because 1.2 is giving 1220, so 1.193 is approximately close to that. So I will make the H for that portion for this density of 1.193 equal to 1200. Okay, you can do actual graph paper. Now the classroom you don't have it. So now you got the H for this. Okay, you got the H for this. Clear? You got the H for this. Now from this, what you get? H for A is 1200. So MMF for A is 1200 into its length. So length is how much length? 0.33, na? Am I right? For that, how much?
Yes, sir. 0.33.
0.33. So 0.33 meters. So how much you get?
396.
96.
80. So now I can draw electrical circuit. This is my MMF source. Here the reluctance of the path A, and here I have a reluctance for this, and here I have one. Okay, so this is B, this is C, and this is A. You know, you can apply the Kirchhoff's voltage law. I mean, it's a magnetic circuit, but you can apply equally those laws, with little modification. So MMF, this one, the source, is the MMF for this plus MMF for this. Clear? MMF for
Yes,
this
sir.
plus MMF for this. So total MMF is MMF for A plus MMF for C, or otherwise you can use this loop, big one. Okay, any loop can be used. I'm using this one, but you can even use this. So MMF for C, or you can put just for understanding also equal to B. Clear? So now what is that? For MMF for is 396, and what is the MMF for B or a C?
297.
297.
97.
So how much you get total?
693.
693. So this much is the MMF required. Now nothing is mentioned, and even they have not asked what the current. Now assuming you have a 500, just I am extending the problem. Now N is 500 if given, then I will be 693 by 500. Clear? So something like that you will get. Okay? Something like that you will get. Clear? Now we can't take many problems. Here we have to stop. So just wait, don't leave. Just wait. See, I'll just go up. Anyway, see, you know, at least in the 12th you studied EMF is N d phi by dt. Okay? Is it not? EMF as per Faraday's law of magnetic induction, electromagnetic induction, N is d phi by, E is N d phi by dt. Again, if I use Lenz's law, it will be minus. Okay? Now, Now, you know E is also equal to L di by dt. Huh?
Yes, sir.
You know this.
Yes, sir.
Yes, sir.
So from these two equations, we can say that L is anybody who can say something?
N phi by I.
N phi by I. Clear? Understood or not? So this is how. Again, there are two types of inductance. This is the self-inductance. Okay? And another is mutual inductance. Normally, L is used for self-inductance and mutual inductance is represented by M. Okay? So, basically, mutual inductance, when we put two coils close to each other, okay? Then if you check current flow in one coil, there is a EMF induced in another coil. Okay? So, from that, we get the new inductance, we call it as a mutual inductance. Clear? So, like that, this is just for your information I am telling you. Huh? Okay? So, mutual inductance and self-inductance. These are the two types of inductance. Again, you will learn these details later on. And as I told you, when you can apply to find out the equivalent of many inductors, when in series or in parallel, you can apply same law as applicable to resistances. Okay? You can use laws which we have studied for a resistor. Same laws can be used for inductances. Clear? So this is just I want to give you an idea about the inductances. Okay? Again here, when we are using resistance law, we are neglecting mutual inductance. It is applicable for self-inductance only. Okay?
Yes.
So here we stop now. You can leave the meeting.